Good morning, grade 9. Hope you are all doing well and being safe. This is Miss Pamela Teeny giving the physics course. Today we are going to continue the general revision. Now we are going to talk about the force of stretched or compressed spring. Springs exert a force when they are stretched or compressed. The force acts to restore the spring to its natural state. A compressed spring pushes outward and a stretched spring pulls inward. As you can see in the figure in front of you, to the left we have a spring that is static. It is not compressed nor stretched. So this spring doesn't exert any force. The compressed spring pushes outwards, which is the spring in the middle of the figure, and to the right of the figure we can see a stretched spring which pulls inwards. This force is exerted to restore the spring to its natural state, which is the static state. Hooke's law. Hooke's law explains how we can calculate the force exerted by a spring that is stretched or compressed. It states that the force exerted by an ideal spring is proportional to the distance of its stretch or compression. So as the distance of stretch or compression increases, the force exerted by the spring increases as well. This can be written in equation form, as you can see in front of you. F, which is the force exerted by the spring measured in newtons, is equal to K, which is the spring's constant measured in newton per meter, times X, which is the stretch or compression distance measured in meters. Note, the larger the spring constant, the greater the force exerted by the spring. Thus, a large spring constant corresponds to a stiff or tough spring. So spring constant is something specific for each spring. The larger the spring constant, the tougher or the stiffer the spring is, and the more force it exerts. So in this chapter, we talked about Newton's laws of motion, and we talked about several kinds of forces that we need to know in order to solve problems including Newton's laws of motion and to draw the free body diagram of a certain object. We talked about the normal force, the weight of an object, which is the gravitational force acting on an object. We talked about friction, kinetic and static friction. We talked about the force in a stretched or compressed spring. And finally, the last kind of force that we are going to study in this chapter is tension. Tension is the force exerted by a string, rope, or wire that is pulled tight. So the force that is exerted in a spring is different than tension. Tension is a force exerted by a string, a rope, or a wire that is being pulled tight. In an ideal string, which is one with little mass, the tension is the same everywhere in the string. So at all points or at all locations in the string, the tension force is the same. Look at the figure in front of you. You can see a wire with a mass attached to it. So this mass pulls the wire tight, so the wire exerts a force called tension. Now we are going to talk about calculating tension. The tension in a rope is equal in magnitude and opposite in direction to the force pulling the rope. So if you're pulling a rope downwards with a force of 30 newtons, the tension in the rope is upwards with a force of also 30 newtons, because they are equal in magnitude and opposite in direction. And you must know that there is a maximum amount of force that a rope can exert. Once it is exceeded, the rope breaks. So let's say I have a rope that can exert a maximum force of 50 newtons. If I exceed this amount of force when I pull the rope breaks. So as we already stated, that the force of tension exerted by a string, rope, or wire is equal in magnitude and opposite in direction to the force pulling the rope, wire, or string. So if a mass is attached to a rope, wire, or string, the force of tension is equal in magnitude and opposite in direction to the weight of the mass. So whenever we attach a mass to a rope, string, or wire, we can find the force of tension in this rope, string, or wire by calculating the weight of the mass, and then the force of tension will be equal to the magnitude of the weight of the mass and opposite to its direction. So the force of tension, as you can see in the equation in front of you, is equal to negative W, which is the weight of the object or the mass that is attached to the rope, string, or wire, equal to negative M times G, where M is the mass measured in kilograms and G is negative 9.8 meter per second squared, of course, on Earth, unless I state otherwise. So look at the figure in front of you. This is a mass attached to a rope. So the mass has a weight that pulls downwards. So this is the force exerted on the rope. And the rope exerts a force of equal magnitude and opposite direction, which is the tension force. So as you can see in the free body diagram, two forces act on the object, on the mass. weight is downwards and tension is upwards, and they have the same magnitude. This is how we can find the tension of a rope or string or a wire with a mass attached to it. Now we are going to talk about equilibrium. If the net force exerted on an object is zero, then the acceleration of the object is zero and its velocity remains constant. That is, if the net force acting on an object is zero, the object either remains at rest, if it was at rest, or continues to move with constant velocity if it was moving. When the velocity of an object is constant, including when the object is at rest, the object is said to be in equilibrium. And the first condition of equilibrium is that the net force, or the summation of forces in the x direction and in the y direction, is equal to 0 newtons. What is work? Work is done when a force is applied to an object and the object moves in the direction of the applied force. So in order to do work, we need to apply force on an object and the object must move due to the applied force. If you look at the figure in front of you to the left, a person is pushing a wall and the wall does not move, of course, due to this person's force. So this person is not doing any work. Now look at the figure to the right. A person is pulling and pushing a desk and the desk moves due to his applied force. Since he is applying a force and the object is moving due to his force, then he is doing work. Calculating work. Work is calculated by multiplying the force applied on an object by the distance that the object moves. Force and displacement are in the same direction. So in this simple equation, the force is in the same direction as the displacement. We will consider other cases later in this lesson. So in this case, or in this equation, the force and displacement have the same direction. This is why we can calculate work by multiplying the force applied on an object by the displacement of this object. So the distance that the object moves due to this force. Work is measured in a unit called joules. Force is measured in newtons, of course, and distance is in meters. So as we already stated, work is when we apply force on an object. So we do work when we apply force on an object and the object moves due to this force. So if the object does not move, we are not doing work. And in order to calculate work, if the force and the displacement are in the same direction, we multiply the force applied on the object by the displacement of that object due to this force. Since we already stated that work is equal to force times displacement if force and displacement are in the same direction, how do we calculate work if force and displacement are not in the same direction? So if the force exerted on an object is at an angle with the displacement of the object, then only the component of the force in the direction of the displacement does work. So we only consider the component of the force in the direction of the displacement. So in this case, if the force and displacement are at an angle to each other and not in the same direction, we use the equation that we see in front of us. Work is equal to force measured in newtons times displacement or distance measured in meters, the distance that the object moves, times cosine angle. Angle is the angle between force and displacement and it's measured in degrees. So here we consider the angle between the force and displacement and we use this equation so we can only consider the component of the force that is in the direction of the displacement. The work that is done on an object may be positive, zero, or negative, depending on the angle between the force and the displacement. So whenever the force and the displacement are not in the same direction, the work that is done may be positive, zero, or negative. It is positive if the angle is less than 90 degrees. If the angle between the force that is applied and the displacement of the object is less than 90 degrees, then the work is positive, as you see in the figure in front of you to the left. In the middle, they are telling us if the angle is 90 degrees, so if the displacement and the force are perpendicular to each other, then the work that is done is zero. And if the angle is greater than 90 degrees, then the work that is done is less than zero, so it is negative. Notes: if an object is accelerating, then the force applied to the object is equal to mass times acceleration. Force is measured in newtons, mass in kilograms, and acceleration in meter per second squared. So, if you need to know the work that is done on an object that is accelerating, you need to know the force. To calculate the force, you use Newton's second law by multiplying the mass of the object by the acceleration of the object if the object is accelerating. Also, if you need to know the work done by gravity, or you need to know the work of a person that is carrying an object opposite to gravity, like in the figure you see in front of you to the right, you calculate force by multiplying mass times g, which is the acceleration due to gravity, which is usually 9.8 unless it is stated otherwise. So if they ask you to find the work done by gravity or the work done by a person that is carrying anything upwards opposite to the force of gravity, you calculate force by multiplying mass times g. The work done by separate forces can be summed. When more than one force acts on an object, the total work is the sum of the work done by each force separately. Thus, if force F1 does work W1, force F2 does work W2, and force F3 does work W3, and so on, then the total work is equal to W1 plus W2 plus W3, and so on. In the figure in front of you, you can see an example of an object with several forces acting on it. In this figure, we can see a box that is being pushed on a table. 4 forces act on the box. First, the gravitational force, which is the weight acting on the box downwards. Then the normal force, which is the surface force acting from the table on the box upwards. And we already know that the normal force and weight have the same magnitude but opposite directions. Then we have the applied force, which is the force that is pushing the box, and the frictional force, which is the force that opposes the motion of the box. Note, since individual amounts of work can be positive or negative, it's possible that the total work may be zero even though the individual amounts are non-zero. In the previous session, we explained that work is negative if the angle between force and displacement is greater than 90 degrees, and work is positive if the angle between the force and displacement is less than 90 degrees, and work is zero if the angle between force and displacement is equal to 90 degrees. So when we add the work done by separate forces, the total amount of work may be zero even if the individual amounts are non-zero, since they can be negative or positive or zero. Now we are going to talk about the two main types of energy. The first is called kinetic energy. The kinetic energy of an object is the energy due to its motion. So any object that is in motion has something called kinetic energy. Kinetic energy is measured with the unit joules, the same unit used to measure work. Calculating kinetic energy. In order to calculate the kinetic energy of an object, you use the equation you see in front of you. Kinetic energy measured in joules is equal to the mass of the object, which is measured in kilograms, times velocity of the object squared, measured in meters per second, over 2. Kinetic energy increases linearly with the mass and with the square of the velocity, so they are directly proportional. Now we are going to talk about the relationship between work and energy. So work and energy are related. There is a very simple connection between work and the change in kinetic energy. Specifically, the total work done on an object equals the change in its kinetic energy. So if you need to know the work that is done on a certain object that has kinetic energy, this total work is equal to the change in the object's kinetic energy. This idea is demonstrated in the work kinetic energy theorem. So the work kinetic energy theorem shows the relationship between the total work done on an object and the kinetic energy of the object. So the net work, or the total work done on an object, is equal to the change in the object's kinetic energy. So the final kinetic energy of the object minus the initial kinetic energy of the object. So in order to calculate the net work, or the total work done on an object, we use the equation that you see in front of you. Net work is equal to half times m times vf squared. So this is the final kinetic energy. M is the mass measured in kilograms. Vf is the final velocity measured in meters per second. Minus the initial kinetic energy, which is half times m times vo squared. So m is the mass measured in kilograms and vo is the initial velocity of the object. You can also write it as vi, whatever makes you less confused. So if the network is positive, so if we calculate the network, or if we know the network of an object, if it is positive, then the kinetic energy of the object increases. If the network is negative, then the kinetic energy decreases. And if the network is zero, then there is no change in kinetic energy. So the final and the initial kinetic energies are the same. The second type of energy is called potential energy. You must do work if you want to lift a bowling ball from the floor onto a shelf. Once on the shelf, the bowling ball has zero kinetic energy since it's not moving anymore, just as it did on the floor. Even so, the work you did in lifting the ball has not been lost. It is stored as potential energy. If the ball later falls from the shelf, gravity will do the same amount of work on the way down as you did in lifting the ball up. As a result, the work you did is recovered in the form of kinetic energy. And you can see this in figure 6.6, page 202. Energy that is stored for later use is referred to as potential energy, or PE. So this is the definition of potential energy. You can think of potential energy as a storage system for energy. So it is a system that stores energy. When we increase the separation between the ball and the floor, so when we increase the amount of work that we exert on the ball in order to lift it up, the work we do is stored in the form of increased potential energy. So if I lift the ball to a height of 2 meters, it will have more potential energy, more stored energy, than when I lift the ball, let's say 0.5 meters. Potential energy has several forms. One of the most common is called gravitational potential energy. The potential energy of an object is determined by the amount of work required to move this object from one location to another, as we already stated in the previous example. So in the case of gravity, the work is mgh, and this work is stored as gravitational potential energy, PE, gravity. So in order to calculate gravitational potential energy, we use the equation that we see in front of us. PE gravity is equal m times g times h, where PE gravity is gravitational potential energy measured in joules, m is mass measured in kilograms, g is acceleration due to gravity measured in meter per second squared, and it is equal to 9.81 meter per second squared unless it is stated otherwise, and h is the height of the object measured in meters. Now the second kind of potential energy, which is elastic potential energy. Elastic potential energy is potential energy stored as a result of deformation of an elastic object, such as the stretching of a spring. It is equal to the work done to stretch the spring, which depends upon the spring constant K, as well as the distance stretched, as you can see in the figure in front of you. This is a spring that is stretched a distance x. So, the elastic potential energy stored inside the spring due to its stretching or its deformation is equal to the work done to stretch this spring. In order to calculate the potential energy of a spring, we use the equation we see in front of us. Potential energy of a spring is equal to half times K times x squared, where potential energy in a spring is measured in joules, K is the spring constant measured in newtons per meters, and we talked about it once when we took Hooke's law, and x is the stretch or compression distance of the spring measured in meters. So if it is given in centimeters or in kilometers, we convert it and then we calculate.